In this video, I'm going to demonstrate how a diode works. What I have here is a linear power supply that I'm building for another series of videos, but I'm going to use this in lieu of a battery to make this demonstration. The way this is set up is I have my positive 12 volts along this line of connectors and my ground along this line of connectors. Think of this like a battery where I have my positive terminal here and my negative terminal here. I'm going to put a light emitting diode in here. Now I can't run my 12 volts directly to my diode because that would be like trying to drink from a fire hose. This power supply can supply way too much current for this diode, so I have to limit my current. So what I'm going to do is put a 1000 ohm resistor between my 12 volts and the diode. And this would be like squeezing the fire hose so that it can't supply as much water, and so this will light up the diode without burning it up. And there we have a very simple circuit using a light emitting diode. So think of this 12 volts as like the supply line bringing water to your house. Brings in water under high pressure, it comes out the faucets, does something, goes down the drain where there's a lower pressure. So we have our electrical current coming in the 12 volts, traveling from positive to negative, conventional current, to the ground, and then back out of the circuit. Now what I'm going to do is move this resistor to where it just bridges this gutter here. And to make this circuit work again, what I would need to do is put a jumper over to this series of holes here to make the connection again, so I will do that. And so now we have that circuit again, but I put that there for a reason. I'm going to take that jumper back out and replace it with a rectifier diode. And here we go. And there's our circuit again. We have our positive 12 volts here. Our conventional current is going to travel from the positive 12 volts through the diode, through the resistor, through the light emitting diode to ground and back out of the circuit. Now watch what happens when I take the rectifier diode out and just simply turn it around. Nothing. So what's happening? Well, a diode acts like a check valve. It will only allow electricity to travel in one direction. This is the anode and this is the cathode. Conventional current needs to flow from positive to negative, so it's going to flow in this direction. But current cannot flow from the cathode to the anode in a diode. It can only flow from the anode to the cathode. So the diode is the wrong way. It's like a check valve put in the wrong way. It will not let the electricity flow. But if I take the diode back out and just flip it around, now I have the anode here and the cathode here, and the current can travel from the positive 12 volts at the anode to the cathode, through the resistor, through the light emitting diode, and to ground. And so you can see that this simply acts like a check valve. Electricity can go this direction through it, but if I flip it around, it cannot go against the cathode. So if you look at the diagram, you'll notice that the arrow shape of the diode symbol points in the direction that conventional current flows. And right now, that arrow is pointing the wrong way. We have the cathode and the anode this way. Current cannot flow from the cathode to the anode. So once again, let's flip that around. Now, notice the arrow is pointing the direction that conventional current wants to flow. So it's able to flow through the diode, just like an open check valve, and current flows through the resistor, through the light emitting diode, and lights up the circuit. Now, this is a light emitting diode, and it's not called a diode for nothing. This works the same way. I have the anode on this side and the cathode on the ground, and if I pull this light emitting diode out and flip it around, just like the rectifier diode, the current will not flow. So the current can flow through the rectifier diode, but now it is blocked by the light emitting diode, which also acts like a check valve. And if I take this out and turn it back around, it lights back up again. Now that we understand how a diode works, how are they used in electric circuits? One of the most common uses for diodes is rectification, which is turning alternating current into direct current. Remember my analogy where I said that this power supply and circuit is like the water pipe coming into your house. It brings water in under high pressure, it comes out of your faucet, does something, goes down the drain, and then back out the sewer, always going one direction. Alternating current would be like one moment the water is coming in the pipe, out the faucet, and down the drain, and then the next moment it turns around and it's coming out the drain, back up the faucet, and out the inlet pipe. Well, that's kind of absurd for water, but it makes a lot of sense for electricity. If we have our electricity going back and forth, we can use a device called a transformer to step that voltage up to a very high voltage where we can distribute it efficiently, and then when we get to the destination we can step it back down to a more safe voltage to use in our houses. However, most electronic devices want direct current. They want the current to be flowing in only one direction. If you can imagine taking the water into your house and storing it in your own tank so that you always get the water flowing in one direction. Well, you could do that with a check valve. Put a check valve on the inlet so the water only comes in when the water is flowing that direction, comes past the check valve, fills the tank, and then you can use the water from the tank. Another possibility is to use a matrix of check valves so that when the water is coming in the pipe, it goes into your tank, and then when it reverses direction, that switches off some check valves, switches on some others, and causes the water when it comes out the drain to also fill your tank. What I've just described here is half-wave rectification and full-wave rectification. To understand more about rectification, you can watch my video on the rectifier for this power supply I've built. As a matter of fact, if you look right here, I have 4 rectifier diodes, which act like 4 check valves, so that when the electricity comes in off this transformer, which is alternating current, it switches these rectifier diodes on and off alternately, so that what comes out is always going the same direction. And this is a capacitor which acts like a storage tank to hold that electricity for the rest of the circuit to use. If you want to understand more about how that works, you can watch my video on how rectifiers work, and that is linked to in the description below. Another use for diodes is any time you want to prevent electric current from flowing from one place to another. For example, you might have 2 circuits that are hooked up together where you have varying voltages, and when one voltage is higher than the other, you want current to flow from the higher voltage to the lower voltage. But if they reverse and the other voltage becomes higher, you don't want it to flow back the other way. And so you could put a diode in there acting just like a check valve to only allow the electricity to flow when circuit 1 has a higher voltage than circuit 2, but it will not backflow when circuit 2 has a higher voltage than circuit 1. Another common use for diodes is voltage clamping, such as preventing voltage spikes on the induction coils for relays and solenoids. That's a bit more complicated than I want to explain here, so I'll make another video just about that subject. So look in the description for a link to that video. Now we're going to learn a little more about how this diode acts to electricity, because we've looked at the fact that it only allows current to flow in one direction, but the voltage and current relationship is also important to understand. So let's start by putting a voltmeter across the diode and see how much voltage we have across it. So I put the red lead to the higher voltage, the black lead to the lower voltage. And if we look at the voltmeter, we see that we have 0.67 volts across the diode. And this is pretty close to the typical voltage. We usually assume that a silicon diode, when it's forward biased, meaning that electricity is flowing in the correct direction, we usually assume that it's going to have about 0.7 of a volt. And here we are pretty close to that. But let's take a look at what happens when we vary the current. I'm going to remove the light emitting diode and the 1K resistor and replace them with a 1 million ohm resistor. Let's see what happens. So let's take this all the way from ground up to the resistor, and we see that now, that's not 1 million ohms. You gotta watch out for these Chinese resistors. I have on my breadboard here a 1 megohm resistor and a 150 ohm resistor. Can you tell the difference? They both look like they are brown, black, green to me. Well, if you look at the bottom resistor, that's my 1 megohm resistor. These are 1% resistors, so they use 4 color bands for the resistance instead of 3. The 5th band is the tolerance. The brown on the 5th band from the left means that it's a 1% resistor, and it also 1% resistors typically have 4 color bands instead of 3. So this is read as brown, black, black, yellow, which would be 1004, which is 1, 0, 0, and 4 more zeros, making 1 million. The other resistor here, which is 150 ohms, is read like this. Brown, green, black, black, and then the brown tolerance band. And so that's going to be 1, 5, 0, and no more zeros. So we have 150 ohms and 1 million ohms. And like I said, that yellow band looks awful green to me. So, okay, let's start this again, this time using the 1 million ohm resistor. And as you can see, we have in the voltmeter in the upper left, we have 0.4 volts across the diode. Well, what's this about? I thought the diode was supposed to have 0.7 volts across it. Remember that 0.7 volts is a typical voltage, but if we don't have enough current going through it, we're not going to get anywhere near that 0.7 of a volt. So we have a very low current going through this diode because of the 1 meg resistor we have in series. So let's measure the current. I'm going to move the leg of this resistor across the gutter so that I can put the current meter in the circuit. So I broke the circuit by putting that leg across the gutter. Now I will complete the circuit by putting the meter in place here. And now you can see that we have 11.6 microamps flowing through the diodes. That's not enough to give us our 0.7 volts. So let's make a plot of the voltage versus current in this diode and see what that shows us. So we're going to put some different resistors in here, increasing the current each time and looking at the voltage and making a plot of the voltage against the current to see what it shows us. So let's go ahead and cut this resistance in half by putting another 1 meg ohm resistor in parallel. And now we see that our current went up to 23 microamps and our voltage went up to 0.42. Let's continue this and continue making the plot of our voltage versus current. So now let's take these out and let's put in a 220K resistor. And so now we have 50 microamps and 0.45 volts. Put that on the plot. Now let's cut this resistance in half again. And now we have 100 microamps and 0.47 volts. So let's put the next resistors in here. Let's cut the resistance roughly in half by putting 50K in here. And we've gone over range, so let's fix that real quickly. Go to the next range on the meter. So now we have 239 microamps and 0.51 volts. We should start to see something happen here. Up to this point it's been fairly flat, but now we should see an even greater increase in current compared to our increases in voltage. Let's move on and see what we get. So let's cut our resistance in half again. And there we have 475 microamps and now 5.54 volts. Go to the next pair of resistors here. This is going to be 10K. And our current is now up to 1,110 microamps or 1.1 milliamps. and our voltage is up to 0.57 volts. Let's cut the resistance in half. We've gone over range again. Let's go ahead and fix that. Now we're up to 2.2 milliamps and 0.6 volts. Now let's put two 1K resistors in series to cut it roughly in half from 5K to 2K. So this is 2K. And we have 5.5 milliamps and 0.65 volts. We're zeroing in on that 0.7 volts that we expect. Now let's make it 1K. 11 milliamps and 0.68 volts. So now let's put this other 1K resistor in parallel to give us 500 ohms. We're over range again. Now we're back to 22 milliamps and 0.71. So we hit that 0.71 volts, or that 0.7 volts, right at about 22 milliamps with this particular diode. But let's keep increasing the current and see what happens. So that's about 500 ohms. Let's put a 200 ohm resistor in here. Yeah, those are getting a little warm. Now we have 55 milliamps and 0.76 volts. Okay, now what I'm going to do is take this out, and I'm going to replace these resistors with a rheostat. Okay, so now I have this 100 ohm rheostat here to replace my discrete resistors. Let's put that into the circuit. Hook up one end to the cathode of the diode. The other end, or should I say, the wiper, is going to go to the red lead of the current meter, and the black lead of the current meter will go over here to ground. And now you see that we have 107 milliamps and 0.79 volts. So we're zeroing right in on 0.8 volts rather than 0.7 volts. Let's increase our current. I'll go down to about 50 ohms. And we've gone over range again. Let me unhook this so that we can set up the meter for high current. Pull the red lead out of the normal socket and put it in the high current socket. Turn it to the 10 amp setting. And now put the meter back in the circuit. And we see we have 200 milliamps and 0.83 volts. So let's decrease the resistance down to 25 ohms and see what happens. So here at about 25 ohms, we've got about 500 milliamps and 0.85 volts across it. Let's increase that up to a little more. See how much we can get out of this. So we've got 1.1 amps and 0.9 volts. 1.3 amps, 0.9, 0.9. Can we get a volt out of it? Nah, not quite. Pretty close, but 0.9 volts. This particular diode is a 1N4005 and is rated at 1 amp and should have 0.8 volts across it at that 1 amp. You can see I pushed it just a little harder and got a little more out of it. There are also commonly available diodes that take much more current and can have as much as 1.5 volts across them. Since we have this rheostat here, let's take another look at this, and instead of watching the resistance, let's watch the current and watch what happens to the voltage. So at 110 milliamps, we have 0.78 volts across the diode. Let's increase that to about 200 milliamps. There we are at 200 milliamps, and we have 0.81 volts across the diode. So we doubled the current, but the voltage did not double. If this was a resistor, if we double the current, we double the voltage. But this is not a resistor, it's a forward biased PN junction. So we get a logarithmic relationship between the voltage and the current. So doubling the current did not double the voltage. Let's double the current again to about 400 milliamps. And there we have 400 milliamps and about 0.84 volts across the diode. Let's increase it to about 800 milliamps and see what we get. So there we are at about 800 milliamps, and we have 0.87 volts across the diode. And if we increase it to our maximum current, we have 1.5 amps and we have 0.92 volts across that diode, getting pretty close to a whole volt. Let's crank this down before I cook my poor transistor here with no heat sink on it. Let's take another look at that plot. Notice that as we increase our voltage along the horizontal axis that we get very little current. But after we pass about 7/10 of a volt, that current starts to run away, and a very tiny increase in voltage causes a huge increase in current. With a resistor, if we double our voltage, we double our current. But with a diode, we have a logarithmic relationship where a tremendous increase in current causes only a tiny increase in voltage. The most important thing to note, though, is that a diode does not always have 7/10 of a volt across it. This is a myth that you've probably heard over and over again. Typically, you might expect 7/10 of a volt across a typical diode, but it is not etched in stone. But if you're troubleshooting a diode, if you think you have a bad diode and you put a voltmeter across it, and you see a volt instead of 7/10 of a volt, is that diode bad? Not necessarily. Look at the amount of current that's flowing through it. If you have a lot of current flowing through the diode, it might be doing exactly what it should be doing. So don't automatically throw out a diode because you don't see 7/10 of a volt across it. Likewise, if there's a very tiny current flowing through it, you might have less than half of a volt. So always double check to see if the diode is actually acting as it should if you don't see that roughly 7/10 of a volt across it. So what have we learned in this video? We learned that a diode is a check valve that allows electricity to flow in one direction. And we also saw that when the diode is forward biased, when it is biased such that current is flowing through it, that when it is in the on state, we can expect about 7/10 of a volt across it. But if we get enough current through it, we can see considerably more than 7/10 of a volt across it. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocademy.net, you can go to patreon.com/join/vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.